Welcome to week 2. I'm Zoe. I'm a senior and a member of Team 3128. In this week we're going to be learning about forces and the basics of motion. So without further ado, let's get to the lesson.
So what is force? You've probably heard it thrown around before, it's like gravity, or maybe you've heard how an object exerts a force on another object. But what is a force? So a force is any interaction that, when unopposed, will change the motion of an object. Or another definition is, a force is a push or pull on an object, resulting from the object's interaction with another object. So, let's do that again. So, a force, when exerted on another object, or force when exerted on another object and is unopposed, will change the motion of the object. So, where do you see that in the real world? So say you're playing baseball and you hit the ball with your bat. So at that point, you are exerting a force forward. You're pushing the ball forward. So then that changes the motion of the ball, and then the ball goes forward. Who knows? Maybe for a home run. So that's an example of like a mechanical force, of you pushing the ball forward. How about another example? Say you're in a sailboat and there's a wind hitting the sail. The wind would be pushing the sail and therefore pushing the boat forward. There are also some non-contact forces like gravity. And gravity, keeps us staying on Earth, pulling us towards the center of the Earth. So remember that. So force is the push or pull of one object to another. And this can result in a motion of the object. Okay. So now we're going to kind of quantify what force is. So Newton, a long time ago, formulated his 3 laws of motion. We're going to be focusing on the second one today. The second law. So the second law states that force is equal to mass times acceleration. So let's break that down. So we'll start with mass. So what is mass? So I'm going to erase this real quick. So mass is basically like the amount of stuff that's in an object. However, this is different than weight, or mass is also known as like the resistance to acceleration. So that makes sense since acceleration is in the equation. So mass versus weight. So weight, when we usually, weigh ourselves on a scale, we are talking about weight. And weight is different because weight can be affected by the forces or the acceleration on an object. So let's illustrate this. So say there's an astronaut and he has a helmet on. So say the astronaut has a certain weight or a certain weight on Earth. But when they go to the moon, the weight's going to change because gravity is different. So gravity on Earth is greater. Gravity is greater. Oh, actually, it's uppercase G. Gravity on Earth is greater than gravity on the moon. So because of that, the weight is greater on Earth versus on the moon. So you can see this when you see videos of astronauts jumping on the moon, or they appear to be jumping, but they're really walking. So what happens is that since their weight is so much less on the moon, when they push off from the ground, when they walk, for instance, or what would be walking on Earth is kind of like jumping on the moon. And that's because they have less weight because there's less gravity. So it's less gravity. And this can also differ on other planets. And this is dependent on the mass, but the distance. But we're not going to talk about that. So weight is affected by acceleration, or in the forces at work. However, mass does not change. So mass is equivalent on the moon and the Earth. And this is important once again because if you look at forces in different places, you need something that remains constant, and that constant is mass. So now we know what mass is and why it's different from weight. So next, let's look at acceleration. We covered acceleration last week with kinematics, but let's review that really quick. So acceleration is how fast velocity changes, or the rate of change of velocity. But first, what is velocity? Velocity is kind of speed of an object with direction. So distance over time with direction. So like a car can be traveling, say, 15 miles per hour north. The velocity will have the direction. So velocity is 15 mph north versus speed is only 15 miles per hour. There's no direction. So bring it back. So now we know what velocity is, and we can remember what acceleration is. So acceleration is how fast does that velocity change over time. And the units for that is usually meters per second squared. So like meters per second, which is velocity, per second. It's in meters per second squared. And these are units for acceleration. So now we know what acceleration is, and now we know what mass is. Good. So now we know what force. So force, according to Newton, is mass times acceleration. Now let's look at how we can kind of predict the amount of force that will be exerted based on looking at the acceleration and mass of an object. So let's do an example of Newton. So you may have heard how the story that Newton had an epiphany or an idea about forces when he saw an apple fall from a tree in his head. However, what happened, or what would happen if that apple was actually, say, 10 kilograms instead of like 2? That's a lot, right? 10 kilograms is a lot. So let's take a look at what that would do to the force of the apple. So if we increase the mass and keep the acceleration the same, right? Because gravity is the same. Gravity does not change. We're still on Earth. Then to even that out, to make that equation true, force also has to increase. So in that case, the apple is gonna really hurt Newton if the mass is increased. However, what happens if, for whatever reason, he traveled to another planet or the moon? In this case, even though that apple has mass increase, force, increase mass, but we're decreasing the acceleration. Depending on what those values are, the force may not change at all because the acceleration changed. Of course, you need to know how much each of these components change to really know how would the force change. But take for argument, say acceleration changes enough to neutralize kind of the change in mass. So the force would stay the same, so Newton's head may still be okay. Alright, so now we kind of covered forces and motion, or forces, and when there's an imbalance in forces, so there could be multiple forces affecting the object, say like there's a person pushing to the right, and a pushing on the left, a box. Let's say person 1 is pushing more, force exerted, then the overall force of the box will be to the right. And so that force will have a motion, cause the box to move. So person 1 would end up moving person 2 and the box. So that's how kind of motion and forces relate. When there's an imbalance in forces, there's causes of motion from acceleration. And just one more thing. So let's look at the units of force. So the units of force is newtons. And newtons is basically kilograms times mass, or times meters per second squared. And this is essentially acceleration and mass. So they're units. And acceleration has a direction based on like negative, positive. So therefore, force also has a direction. And this is something that's important to keep in mind. So, like the force going right versus a force going left. All right, so that's forces and motion.